going to demonstrate the page cache lab. I want to go through a little bit about clean, active, and inactive data. In particular, there's something called swappiness that says how quickly we rotate our data from active to inactive. Clean data is data that's coherent. It's the same in memory as it is out on a RAID device. The key thing I'm going to do in lab here is play with dirty and write-back data. And I want to start getting into the flush daemon. Up till now, the flush daemon's kicked in. We did a little bit of playing with this yesterday. The behavior of the flush daemon has changed in the last couple of kernels, and you're not going to see the exact same behavior. That's one thing hard about a class like this. Every kernel is a little different. And that's also why I like to run the latest kernel to see if I can catch things before it is released or out in the field. The key thing I want to play with in lab is the flush daemon is dealing with dirty data to basically a sync command will flush it, or sysETL parameters. So I want to talk about dirty ratio. Dirty ratio is the maximum that my dirty write-back NFS can get to, and is too big on our systems. Large memory machines, we need to drop that down. Also, dirty background ratio. Now, dirty ratio is the point at which processes are put to sleep doing I/O. Dirty background ratio is the point at which we start flushing. Now, that has changed with the last two kernels. We actually start flushing as soon as the process starts writing. Personally, I think that's a bad behavior and needs to get fixed. I think it's a bug. I don't want to start flushing. I want a delayed write capability, so if I do a read-write, 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 I don't have to flush it and do physical I/O for something that is just modified. I don't want to see write cancels. So I needed to demonstrate this to show you that dirty background ratio changed its behavior. Now, if I actually killed the process, then the flushing stops as long as I'm below background ratio. So again, background ratio is the point at which I start flushing data asynchronously. The process keeps writing. Dirty ratio is the maximum that I can have incoherent and dirty in memory. Now, I did have a site that didn't do things or understand things correctly, and they dropped dirty ratio down to 5, and background was at 10. What this resulted in is once I got 5% of my memory dirty, the entire system went to sleep, stalled out, waiting for the I/O. All the I/O became synchronous once they hit dirty ratio. So those are the two most common that you're going to drop. Also, I'm going to test the dirty expire centiseconds, but that's a little hard to test because I can't stop the flushing unless I kill the process. So I want to see how that works. But normally what I was doing was setting dirty ratio and dirty background ratio to 50% of my memory. That's the maximum they can go. And then putting the dirty expire centiseconds, which is 30 seconds by default, out in the minutes range to stop flushing. And then I would keep my dirty data below these thresholds so that I wouldn't flush by percentage or something, and then drop expire centiseconds back down and see it flush. The other one is write back centiseconds. That's how often the flush daemon wakes up. I would not normally advise changing it. I don't want to wake up too quickly. But there are markets, video surveillance data coming down that you might want to have flushing more aggressive. What I don't want is a flush choke where everything stalls out while I'm flushing. And we were experiencing a flush choke yesterday, huge write-backs because I was writing to NFS. Couple other parameters. Overnight, I modified min slab ratio. That's what created my 99% of my memory being the slab. There are cases where on the metadata server, you might want to have a bigger slab. But again, a bigger slab has problems if I need to trim it. So you don't want the slab to get too big. Another one that I could have played with and I'll try tomorrow is Vfs Cash Pressure. This says when I'm in a trim situation, do I favor the cache or do I favor the slab? What am I going to trim? Am I aggressively trimming the slab or am I aggressively trimming the cache. And swappiness says, do I aggressively trim the cache or do I aggressively swap? Now maybe I'm going to go to a whiteboard here. So we had min underscore, what was it? Vfs Cash Pressure was the one I wanted. Vfs underscore cash underscore pressure. The other one was swappiness. Let me share my desktop. I'm going to go to www.linuxinsight.com, proc underscore sys underscore hierarchy. This is mentioned in the workbook. It's the VM group. So Vfs Cash Pressure. Controls the tendency, the favorability, the tendency of the kernel to reclaim memory, which is used for directory and inode objects. A default value of 100, the kernel will attempt to reclaim directory entries and inodes at a fair rate compared to the page cache. Decreasing this pressure value causes the kernel to prefer to keep D entry and inodes in cache. Increasing it above 100 causes it to prefer to trim the kernel D entries and inodes. The default was 100. So increasing it causes it to protect the slab. Let me go back here. Protects metadata in the slab. Decreasing less than 100 protects the cache and is an aggressive trim of slab. I'm going to double check that with what I just had. Decreasing it causes the kernel prefer to protect the D entries. Less than 100 protects the D entries. I got it backwards. Sorry. Go back to the description again. Vfs underscore cache underscore pressure. I'm just going to, you won't see me bring up the web page because I'm not sharing my desktop, but let me try it again. Decreasing it causes the kernel to protect the slab. Less than 100 protects the slab. And aggressive trim of the cache. Less than 100. If I'm greater than 100, oops, then we were protecting the cache and have an aggressive trim of the slab. I'm going to double check it again. I'm just reading the description. Increasing it causes the kernel to reclaim the slab, trim the slab. Greater than 100 is aggressive trim of the slab. Yep, that's right. Then we got swappiness. And this is a trade-off between the cache and the process space. So increasing causes more process swap. So this is protecting the cache. Decreasing causes more aggressive trim of the cache and less process swapping. Now the default is 60, and the default up here was 100. So if I have find and I have large slabs and LSs, lots of metadata, but I don't use most of it all the time, I'm probably going to want to increase my Vfs cache pressure to like 200 to give me an aggressive trim of the slab. If I am in the batch market with applications, I don't want the application to swap, and I would drop the swappiness down to like 0 so that I aggressively trim the cache rather than swap processes. Now, when I'm on my laptop and I got all kinds of things open or in the background in the browser, it makes sense to have 60 by default because I got inactive stuff that's not being used. So those are the two key things that I want to talk about. We also have XFS sync D centiseconds, how often we flush metadata. That's for metadata. And metadata and data are flushed at different rates. I also want to get a SAR-B to look at my logical and physical I/O. And I've already been doing this a couple of times, LSOF to find open files. What are some of the common buffer cache problems? First one to talk about is what I called write pollution. Lots of dirty data. So if I read 10 gigabyte file, then someone writes 10 gig, my data in cache might be gone. The other thing that we have when you had a lot of this, I called it a flush choke. We experienced that pretty bad with NFS the other day. There's going to be lots of dirty write back, NFS unstable. All procs go to sleep. And file system can't keep up. Another one that we have been experiencing is what I call cache domination. This is when I can't get a buffer. And XFS, oh geez, XFS has buff statistics, and we've been experiencing that and seeing that. Another possibility is what I call cache thrash. This is file system buffer cache file system buffer cache thrash. That's where physicals are greater than logicals. I also refer to it as an upside down cache. This might be a read, trim, read, trim, read, trim situation. I can't hold both data and array, let me call it file and array in memory. So I end up doing, I read the data, but then I grow to process the data, resulting in a trim of the data. Then I have to read the data again, trim, read, and I'm doing more physicals than logicals. By the way, another problem with cache domination is during a trim and cache is shrinking, it's harder to get a buffer. Another thing that we were experiencing here is a NumaLink interconnect. The NumaLink busy from writes. We also saw it with page migration. The compaction was tying up my interconnect, and we actually saw the I/O stall out from that one. And lastly, another common event to worry about core dump storms. And there is in sysctl a core plus PID that would give me a core file for every thread, and if I'm on a 4096 CPU system, I'm going to have a lot of core files generated. But there's also the ulimit limit core size. If it's 0, we're safe. So there are buffer statistics in the proc fs xfs stats file. I had an xfs stats script I was using. You look at that. Buffers are busy or locked, things of that sort. During break, we did a BC free to trim the slab. I'm going to play with the cache in the next day as well. And then tomorrow, we need to get it into a CPU set mode. So tomorrow morning, I'm going to reboot the system and go to CPU sets. Now, BC free is actually calling VM drop caches to do the cache trim. I think I used that earlier in the week. Again, tomorrow I need to get into cache and slab handled in the CPU set. Basically, cache and slab cannot go outside the CPU set. There's a setting that allows it called mem hardwall, but that does not work. The hardwall is always up. And getting into the cache memory management logic, in other words, flushing, and we need to look at that. And lastly, talk about trickle. Oh, that should be trickle flush versus a flush choke. I meant that to be a trickle flush. And we're going to see trickle flush happen right away. So when I start writing data, rather than letting the dirty data get ahead of me, I want to start flushing right away. But I don't want to flush too quickly in case it's a read-write, read-write, read-write situation. So when I oversubscribe my system, page cache has a limit as well. So as you start oversubscribing the page cache, we can get into buffer cache thrash. That's where the data space and the file space don't fit on node. I can get into heavy writes that will basically get ahead of me, and suddenly all my memory is dirty and I can't get memory for anything. I also get a core dump storm, and lastly, everything going busy. So at this point, let me go to my desktop and go through the labs. Let's see. Let me just get rid of the prior PM chart I had. I'm going to start over with PM chart again. So page 9-1, I do have to be careful about var temp filling up and what I use to generate the I/O. But the first one was, first of all, I want to open up a view with CPU utilization in it, just because I like to see that. I'm going to create a second tab here, call this one Memory. Let me make this bigger. Now the workbook's a little bit old in what I might be plotting, so I'm going to plot a little bit more than that. I'm going to go open to New Chart. Then I've got a user-defined view that I want to make. I'm going to start, the workbook started with slab, but I'm going to go into mem util. I don't want to start with slab these days because if slab is big, I can't see it. There's nothing in PM chart that says start at 0 on the y-axis. So something that's small, I'm going to put as page tables is the first thing. That kind of holds my 0 origin down in the lower left corner. Then the workbook has the slab coming in. Oops. That's the kernel heap with inodes and directories and stuff in it. Then I'm going to do dirty. Dirty data is what we're going to be looking at in the lab exercise. I like dirty to be red. Now when we actually do a sync command or the flush daemon comes in to do a flush, then it's marked as write back. That's data that is in the process of flushing. If you see write backs, your file system isn't keeping up to your flush rate. You might have something that maybe is a terabyte times 10 process running and it's constantly checkpointing itself faster than the file system can take the terabyte checkpoint file. Now the workbook has cache clean next. I'm not going to do that. There is a newer metric that's been added now called NFS unstable. I'm going to add that in. That is data coming that went dirty right back and is going off to the NFS server. I'm also going to add in buffmem that's not in the workbook, which is my raw I/O. Now I'm back to where the workbook is. Anon pages is next. And nowadays with transparent huge pages, I also have to have a anon huge pages number for any anon pages that are huge pages from a transparent allocation. Then I'm going to go free. And I'm not going to bother with swap cache that's in the workbook anymore. Now again, I don't like free being blue, so let me change that to a green. Nice bright green there. And let me change anon pages to be maybe a blue. And let me go to anon pages and make that like a light blue or something. That's all just personal preference. There we are. Now, one of the problems here now, I still didn't do it right. Let me cancel. Let me edit chart. I want this in a stack bar, not a line plot. So I can see all my memories free. I also want to get a, actually the workbook had them all in the same chart, so let me open a view here, add in CPU, and I also want to add in disk. I want to see when the I/O wait occurs, when the system time occurs, and when the flushing starts occurring. I want to see when the disk activity actually starts. Let me make this larger. Let me change my samples. Now, when I'm looking at data, I don't like them too wide apart. I actually like them a little bit more narrow than this. So top of page 9.2, I've got a program here called code7.c that I'm going to run. I could also use DD to do the same sort of thing. I don't want to do it on the serial console in case I need that for something. Actually, that one's dead. Here we are. What I'm trying to do is generate some dirty data and watch it go from dirty to right back to NFS, or not NFS right now, but dirty right back clean. Watch when the disk activity occurs and watch what happens to the process during the life of this I/O. PCC on code 7.c. Okay, so I've compiled it. Now I want to run it. I'm just going to call it a.out that I used as a default here. And let me get another window up so I can bring up top. And I think I might actually do another one here too to get top I/O. Okay. Let me fire off this program. I'm going to get rid of free up here. There I can see that the program started writing red dirty data. Look at the disk activity that went down here, and also look at the system time, and then it rolled into IO8. So our disk activity started right away. Now the intent of this lab was to show the effective background ratio and dirty ratio. I want to do something here and just kill this thing. And notice that my dirty data is just sitting there. I still have flushing going on down here, though, even though the process is gone. In fact, we just got an increase in the flush traffic, and now it's done. And there's the flush. So this is kind of hard to explain in the newer version of the kernel because that flushing is starting right away. It should be flushing when I hit dirty background ratio. So while code 7 is running, let's check for the file here. Let me run a.out again. So there I can see the a.out running. Let me quit out of there. LSOF, grep for a.out. Taking a little bit to do things here. There's that dirty data being generated. Now the disk activity actually started a little bit later this time. A.out's still running. Okay, we did get the LSOF. Notice that it's got a file here. If I do this again and do a sort -K on column 7 and then a numerical sort, ignore bleeding blanks, and reverse the sort. And try that again. So I've sorted by this column, and I can see this file here, and it is 9 gig in size. Assuming that the file is open, you'd still be able to see that file. Can you catch the file that Code 7 is writing to? It's writing into var temp. Let me go into var temp. Let me RM the sorts here. And there's the file that we just created, ls-l on 4.1. And in this case, we only have 5 gig of it so far. Okay, that out is already finished. When the I/O is done, how big is the file and how much memory did it take? It says compare and run code 8, so let's do it on code 8. It says step 9 really, but it's really the next step. I want to compare code 7 and code 8. Everything looks okay there. Let's see. Oh, you know what I missed in all this? My drawing? Cache clean. I don't have cache clean in this drawing. That wasn't added at the time. Let me add into there. So it was in the workbook, but for some reason I forgot it when I was looking at it. Did it get added? No, it didn't. When I'm flushing the data, it's going to go from dirty to write back to cache clean. Oh, it's coming up down here. That's not what I wanted. I need to edit chart. Let me click on it first to make sure I got the blue over here. Edit chart. Metrics. Let's add in cache clean. Actually, let me do this. I'm going to get rid of some of these and add them back in. So I wanted it after NFS unstable so I can move it, see it move to clean. Then after cache clean and on pages, I was going to do buff mem. Then a non pages, non huge pages, and then free. I don't like the colors here. Let me go back. Edit chart. I ended up wrapping on colors. I don't know what happened here. It put them back in the original order anyways. Had that happen before. I'm not going to pay attention to that right now. But I don't like the non-pages being the same color. Let me change that to a light blue. Okay. Go back here. Let's do a BC free-A. Do an RM on that 4.1 file. some of this other stuff in there. Okay. Oh, I needed to get code B as well, or code 8. Let me copy. Yes. Now if I do a diff, code 7.c and code 8.c, the only difference in between them is at the end of it, 7 is going to remove the file, unlink it. That's going to result in the cache being cleared once I remove or RM the file. Code 8 is not going to do the remove. That means that it will stay in the cache. So let me recompile these things. Oops. So let's run the code 7 again. Notice code 7 doesn't have any WChan. It's currently showing running. There's the dirty data that it's generating. There's the disk activity that started flushing. There's code 7. I am seeing some journaling. Code 7 is now, looks like it's gone into a sleep state. It's back running now. But we do have some I/O weight associated with the journaling activity. This is on root, and root is an extended 3, so we're actually seeing all this I/O kicking in now. So at 1.5, 2.9, I'm seeing this GET request on the journal, log weight, and code 7. There, GET request. Add in the free again. Can't really see anything with the free there. Little bit of I/O wait time in there. There's the disk activity. Looks like our process is finished now. Notice there was a flush here, and it went from red to this brown here, which was the cache clean. So once we flushed it, if you look at this, once we flushed it, it went from dirty to clean. The light blue is just my process space. So there you can see the file actually got to about 10 gig in memory. And code 7 is done now. Let's try it with a code 8. I can see system time associated with this. Now it's flipped over to I/O wait, and we can see the disk activity starting. Now, it didn't start right away, but we were at about 2 gig before it started flushing. There, we just had a flush where all that dirty went to write back. Or I'm sorry, cache clean in this case. Can we see the write backs in here too? Let me get rid of the dirty, the slab, cache clean, anon pages, buff mem, page tables. There's the flushing. There's the write backs, and the write backs are getting only a meg or 2. Let me put the dirty back in. So you can barely see the flushes occurring. Might even want to put them on a separate chart. Like, let me do that here. New chart, mem, util. Right back. me change that to a stack bar just to make it easier to see. It looks like my dirty is topped off. So as the right backs, notice I just started the chart so we can't see the right backs before, but the right backs have finished and the flushing is finished and my dirty data is gone now too. It should have gone into cache clean. So here you can kind of see where that file topped off at 10 gig. Any questions right now?
No.
The LSOF to see the file, we were seeing it go from dirty to write back to clean. 7 removes the file when it's done, so we see everything released, whereas code 8 does not remove the file, and therefore it stays in the cache as cache clean. A BC free will trim it, or removing the file will trim it. Let me go into /var temp, remove that file. It's basically the PID of the code. And there we can see the cache clean got released. Let me do it again. This time, though, I'm going to do a DD this time. We just put it into temp. So there's our dirty starting. Wondering when the flush is actually going to kick in here. So there's a little bit of flush down here, kind of buried in the noise, but we've started flushing right away there. It's stalled out at the moment. There's no flushing going on. Now we just got more right backs. This is where you can actually start seeing the wake up, the right back centiseconds value in terms of how often the flush demon is waking up and looking for stuff. There we just had a flush and everything went from dirty to cache clean. There's the right backs that had flushed, the disk activity for it. Now this file is going to keep growing. The question is how far it will grow. Anyway, in the workbook, BC free on step 10 will clear up the cache. Difference in memory between 7 and 8. 1 removes the code when it's done and the cache is cleared. The other step there, I want to, 13, can I remove the file before the I.O. is done? So here we can see the flushes, we can see the dirty. I've only got 1 thread running. Let's see what happens here, though. I don't want to do it on that one. Pick another window here. There's my DD. My DD is asleep now on that GET request. And we've got journaling activity. And by the way, I can see the flush daemon also flushing here. 8:0 is the major minor number of the file system. I do a more on proc partitions. Oops. 80 is SDA. So, it was in temp. Let me go into temp. That's taking a little bit here. There's that dirty data. I just want to see what happens here. RMX. This is always dependent upon the kernel. Sometimes the RM will sleep until the file is flushed. Now what happened? I still have that data. In fact, I should do a watch Vf-H on /temp. And let's see what happens. I'm not even sure that if I wanted in G's or something. So I still have a dirty data. I still have dirty data here. My DD is still running, even though the inode for the file has been removed. The actual file and disk space allocated to it has not been removed yet until the flush is done. And my memory use continues to grow. You can see the periodic flushes occurring here. You can almost see the write-back centiseconds of when the flush daemon wakes up and flushes stuff. So step 13, I did remove the file. When does the RM finish compared to dirty? So the dirty's still growing, the cache clean's still growing. I did remove the inode for a file that's being flushed too. But the cache clean and the dirty on step 14 are still growing. The process itself is still growing. I just don't have an inode to it. Now the next part is kind of hard here. We basically want all of memory cache data, cache clean. Let me do something else before we go to that part. Let me kill this off. Cannot kill it until the flush is done. Kill all DD. Let me do a -9 on DD. Still there. Oh, looks like it was running. Looks like we got it killed. Finally got it killed. Let's see what it's got in memory. And it looks like all of our dirty and write-back finally got released because, again, I had the file removed. Okay, this time, let me go into Home, PNG02, I believe. I've got a file here. Let's see how big it is. 200 gig file. I'm on a 200 gig system, so let me just do an MD5 sum on that thing. That's going to read the whole file in. Now before I was using MD5 sum on /dev, and that showed up as buffmem. This time I'm doing it on a file through the inode, so that should show up as cache clean. Unfortunately, though, it's also off on NFS. So if I do a crash, I'm not really seeing anything happen yet. Keep free out of there. PS, grep for MD5 sum. Do a BT on it. That's showing it running. There's a sleep. There we can see it doing an NFS read and going to sleep. And again, this would get counted as IO wait because it's in the IO sched block. This may take a little bit for this to actually grow because it's NFS. Let me go off and see if there's another one here. Let me do an MD5 sum on these biggest file. I'm just trying to get the cache to grow. All of it clean. All of this stuff is just reading everything in. No dirty, no write back. I can see the cache is growing. I can see the reads coming from disk now. This will be a little bit faster than coming in from NFS. While that's growing, slab top dash S space C. Look at where buffer head is right now. I want to watch what happens to that. We're at 51 meg. If I'm reading this file in as cache clean from a read, if you were to run code 8 a bunch of times, it's not removing the file, and every time it runs, it generates a 10 gig file. So in your systems, running about 10 of them should fill up your memory with cache clean. That's step 15. Now what I want to do is step 16 is push the memory down and recover that cache clean. This is where swappiness would come into play. So let's wait for this to read all of the that 200 gig file into memory and be all cache clean. And then we're going to try to trim it. Now before we were trimming a huge slab that was like 200 gig. Now we're going to try to trim a clean portion of the cache. That should be a lot easier to recover. I think I want to do something else here while we're waiting. Add a tab. I'm going to go into active, inactive. So here, let me fill out a report, a chart that's going to take the active and inactive. Let's see, util. Inactive file. Active file. Inactive anon. And active anon. Make this a stack bar chart. So I do see that I have a large inactive file cache. This is the stuff that we're reading from MD5 sum, but since we're not going back to it and rereading it, it's still all marked as inactive file. Do something else here. Another tab. Call this swap. This is where swappiness comes into play. Let me get rid of free. Nothing out on swap that's used right now. How's my memory doing? I'm still only at about 60 gig of my memory being cache clean. Let me bring free back. And most of that cache clean is yellow or inactive here. Got a little bit of active file, inactive anon, and active anon. So I need this to get big enough, and then I want to push it down. Notice buffer head is slowly growing to describe this cache page. So I'm waiting for 15 where all the memory is cache data, all cache clean. I'm going to try to push that down. You could use code 4s or you can use memhog. Step 17 then is to run both. If I'm writing a whole bunch of data and trying to grow memory at the same time, who wins? Does code 4 get the memory from dirty or not? Can we push it down? Let me do a couple of checksums on the same file. I do see a little bit of system time associated with this now. Let's bring up top. There's all the MD5 sums all running, but there is 10% system time here. Let's find out what that 10% system time is. Perf top. Copy user generic string. Find busiest group. Let's try a perf record -G. Oops. -A. Good enough for me. Perf report. So that copy user generic string, it is in the kernel, expand it. So it's some sort of read, but this copy user generic string is where all my system time is. Let me do a top sys. Oh, starting to get some checksums back. Okay, well, I'm seeing GNOME session index VNC being the main system times here. I'm not seeing MD5 sum or anything like that causing the system time. Yet here it does show MD5 sum being the top. Metacity's in there way down doing a lookup. But these are all the top two. And this was the main one here. Copy generic string, file read actor. And it's async IO, it looks like, too. How's my memory? We're waiting for memory to get stacked up. Still waiting for it to go. I'm just trying to get that biggest file all read in memory because it was a 200 gig file. Some I/O wait time going on. In actuality, it looks like my reads have stalled out. Some contention somewhere. Things are going to sleep on an I/O wait. Not seeing it there. Let me do an I/O top. You can see that those MD5 sums are doing the most amount of I/O, all reads. %, system time. Not really seeing the system time in this stuff. But perf top is still showing it as that copy user generic string thing. And put page. We did have IO8 showing up now, PS-E, grep for D, PSEL, sorry. So there we can see some MD5 sums, they're sleeping. You do an echo T into /proc/sysrq trigger. Still waiting for more memory. Trying to get all my memory. It's a little easier on your systems that are smaller in memory. I am starting to have trouble getting some things going here. Top isn't running. I do have no response there. I do still have PCP working. I didn't grab Numalink though. Let me add another tab here. See if the interconnect itself is too busy. Not a whole lot of Numalink traffic there, 200 megabytes per second. It can handle more than that. I have a lot more things that have fallen into IO wait. I am seeing some writes going on out to disk 2. Crash. Saw some MD5 sums in there. I want to try to catch one. Uninterruptible 61218. There's an example. This one is actually on an NFS. I'm not sure why I would be going through NFS. Let's see, that's a PID of 61218. Let's take a look at that. That's just on a big file. Wonder what the current working directory for that thing is. I'm going to go into /proc 61218. And cat the EN, let's just cat CWD. That's not even helping me. Just wasn't sure why I was looking for NFS, unless that's the one that I was running off the NFS server originally. Process go away. All we're trying to do is pack up memory with cache clean. Let me do a kill all MD5 sum. My CPU utilization came back. My disk activity is stopped, but I still have a large cache. Slab top -S space C. The buffer head, it doesn't look like it grew too much actually. So now let's try memhogs. Let me just put up a bunch of 20 gig ones. Oops. I wanted 20 gig. There's my anon pages and anon huge pages. Look at the system time associated with them. That's all from the allocation for these things. Also seeing writes off to disk, huh? My Numalink traffic went up from the allocation and the touches. I do have stuff going out to swap. It's real small. So that's the writes. Now, one thing that is going on here, if I can catch this, is sysctl-w vm.swappingness equals 0. Oops. And that should be more aggressive at trimming. Notice it stopped my swapping so that applications were swapping. Instead, I had more aggressive at trimming my cache. That was a good example where swapping as being low stopped the swapping of the processes. And can we catch an aggressive, can't really see an aggressive trim of the cache. These things are also stuck on system time. All raw spin lock IRQ, clear page C. This does not look like compaction, and in fact we had compaction turned off earlier. I haven't rebooted. I do see some shrink page list going on here. Let's see what that caught. Perf report. All that system time again coming from memhog was that raw spin lock IRQ. There was also clear page and zone reclaim. Let's just expand this. Remove mapping, shrink page. It was all about shrinking the page list. Page cache. It was all that system time appears to be the trim. And we're just about out. Notice, let's see if the system time goes away. Some of these things now have moved from system time into IO wait. We're pretty much topped off on memory now. And all that system time went away now. Now we're just in an IO wait state. All that system time we see there looked like, as we were looking in the short interval, to be all in a shrink page, remove mapping, raw spin lock IRQ and event. So having a large page cache and trying to trim it, in that case it took me, I'm looking 15, 18, about 3-4 minutes for me to trim 200 gig of page cache. Quiet the system down. So the next one on 18, step 18 on page 9.2 is basically if we run them all at the same time, trying to do dirty and trying to do memhog or memory growth, who's going to win, who gets memory. So So there I cleared up all my anon pages. Let's see about swap. And swap also got cleared up. Active and inactive. Look at here. Here's my inactive file, so we can see the inactive file being trimmed, and then the active file. And here was my active anon getting more and more as it pushed down, and very little inactive anon. It's kind of hard to see here, but I flipped over, or was it? I turned off the swappiness down to 0, but we can't really see it in here. So here we can see the trim, both the inactive file and the active file, but the inactive anon was not being trimmed much. In fact, it looked like it was growing after I changed swappiness. I can change swappiness to 100 and try it the other direction too. And my NUMA link is now down. We were pushing 1.5, 2 gig on the interconnect during that event. And I do still have stuff out on swap. Let me clean that up. Now the next step is going to be to play with the dirty ratio, dirty background ratio. That's not going to work as expected with this newer kernel. So let me give it a shot here. So I want to be able to generate a lot of dirty data. Determine how much physical memory your system has. I had 256 gig of memory. Run code 8 again, and while it's running, observe PM chart. We've done that. Using disk activity and dirty memory number, how much memory is dirty when flushing starts? This is the thing that's changed. The flushing is starting almost right away. We are not hitting dirty background ratio like we should. And how much of total memory gets dirty? So let's try that. I'm going to use DD in this case. Just trying to get a bunch of these running. Don't really care what naming I'm using. See what we got going here. Go to memory. So there's the system time associated. Now this time the system time is going to be I/O, not trims or something. So here I see memsets, mutex spin on owner. Let's try a perf record -A-P G, I mean. I want to see how much memory I can get dirty. Now notice we did start some write backs and flushing right in here. It was a little bit more right after. It didn't start flushing right away. I'm going to have to take a look at that a little bit more closely. So my dirty continues to grow. System time associated with that. There's that mutex spin on owner, which is all XFS file buffered AIO write. There's all write going to sleep on this mutex lock. Now it kind of looks like our dirty is topped off here. Let's check this, cat/proc/mem info. My dirty has topped off at 65 gig out of 264 gig, it looks like. Let's see if it's going to grow anymore. Looks like it's pretty much topped off right now. Just probably script it. I'm not able to get that dirty to grow any further. Notice there is cache clean coming in now. So if that dirty topped off, and that dirty looks like about 60 gigs still. I have to include NFS unstable and write-back data in this total here. I'm going to mark that as 65 gig there, 300 meg for write-back. I shouldn't have anything for NFS right now. Or was it down here? NFS unstable 0. So it looks like my memory is topped off here. Now let's compute what's going on here. sysctl-a for dirty. So my dirty background ratio is 10. That's when I should start flushing at about 25 gig. Now I see the write-backs here. There were some write-backs here, but it's going into an aggressive swap at this point. Or I'm sorry, aggressive writes. But again, that 65 gig, let's try the dirty ratio is 40. Let me bring up my calculator. So let's take 256 gig times 0.4. That says I should be able to get 100 gig dirty before things go to sleep, but that appears to be off a little bit right now. If I go to top, I can see things. These DDs have been put to sleep with the GET request, and that's why I have high IO wait time. Let me try something, sysctl-w. It cannot go larger than 50, so I'm going to set that to 50. I'm also going to try to set the dirty background ratio to 50. Now remember, I'm still also flushing by age. Let's set that out of the way. This is how often things are waking up, so a 5-second window is the size of the wake up of the flush daemon to decide if anything is over the threshold, like over 30 seconds. So let me do a sysctl-w on, this is all bad, I'm just trying to show the effect here. Expire underscore centisex. And let me just make it really big. Notice when I did increase my dirty ratio, I did get more dirty data in the system. Let me see if I can kill all this stuff off and try again now. So step 4, it looks like I only got 64 gig dirty when in fact it looked like I should be able to get 100 gig dirty based upon dirty ratio. Step 5 on page 9.3, bringing it up top, the WChan field was showing a GET request. Now they're running code 8 to figure out when it goes to sleep and how much memory is dirty. I was using DD as well. And to watch them go to the GET request and become IO wait, and we had IO wait through this whole interval in here. And that started pretty much right here when we were at 64 gig. Notice when I upped dirty ratio, I did get more system time associated with it, and then it went back into an IO8. And at this point now I've killed the processes, so we won't see any IO8 from them, but I still have all that dirty data. Let me try doing a sync and see if I can flush this out. So step 7, I've basically set everything very high so that I don't see the effect of flushing. And then I want to be able to see it by age. So then step 8 is running the code again, and while it's running, observe PM chart, see when it starts flushing, see when it goes to sleep. So we ought to be able to see a lot more dirty data before we start getting write-backs. But right now, I've got to wait for this particular event to finish. And notice all those flushes are going off into cache clean. Even though the processes are gone, we still have to deal with this. I wonder what IO top would show me. Oops, the sync is on that one. So there aren't processes alive to actually account for it other than the flush daemon there. 251:1. Let's do a more on /proc/partitions. And that's PM1 or, I'm sorry, XVM1, which is our scratch file system. Notice the sync itself is stuck on write back. Let's go into crash. So right now I'm trying to, with step 12 and 13, write data that is less than dirty ratio, dirty background ratio, so that it does not flush by percentage of memory dirty. And then look at 15, where I've upped the centiseconds way, so I shouldn't be flushing at all, except right now I've thrown in a sync to clear up the prior data. And I've killed the processes. I can't remove the file. That flush data still has to be dealt with. I think we should take a little break here. Let's come back at quarter 2 and wrap this up. Okay?
Okay. Yeah.
And maybe this dirty data will be gone by then. So
Okay.
we'll see in about 15 minutes.
Okay.
Okay.
Okay, are we back? Anyone back yet? Anyone back yet? Anyone back yet? Anyone back yet?
Hello?
Hello? I was waiting
Hi,
to hear.
is Erming
Yeah,
here yet?
Erming's not around yet. Erming, are you
Okay.
there? I've just been kind of waiting a few minutes here. Erming, are you there yet?
I ran into him. I went over the sub building, and he was over there too. He was grabbing some lunch.
Okay. We'll give a couple minutes for him.
Okay.
That sink did finish a little while ago.
Mm-hmm.
What I was going to do I had to wait for the sink. There's no point in sitting here waiting for that. But the last thing I was going to do then was to see if the expire centiseconds will work. So I'd set the dirty ratio and dirty background ratio real high, and also the centiseconds real long, so we should actually be able to do some I/O, fill up some dirty, and not have any flushing occurring. Then drop centiseconds back down and see the flush happen again.
Okay.
But having a lot of dirty data can get you into trouble quickly if you notice. And here I'm only in the 50 or 60 gig dirty data. Imagine 8 terabyte of dirty data. Dirty ratio, dirty background ratio, we generally try to drop down. And there is by... Irving, are you there? There is by bytes as well. So percentage isn't always fine enough resolution for a large memory machine. So I'd set background ratio high to 50, set the dirty ratio to 50. This is what's not behaving properly. Basically, I'm saying I'm seeing the flushing start right away when the process is started. Been seeing this for the last 2 update kernels. Before that, things were the way I normally expected them. I also then increased this expire centiseconds. I think I'm going to do something here as well. Let's extend this one. And slow down the flush daemon. Doing all this just to see the effects. Herming, are you back yet?
I'm back.
Okay. So like
That's
I
when
said,
for some lunch.
that sync was going to take a little while, and I figured let's just take a break for a while. I'm just about finished. What I was trying to do was show the effects of dirty ratio, dirty background ratio, expire centiseconds, and just to kind of slow things down. And what I'm trying to do is stop flushing, completely stop it, and keep my dirty data below the thresholds of dirty ratio, dirty background ratio, expire centiseconds. That's the intent. Oh, there was one more I should check. sysctl-a for XFS. Let me do a sysctl-w. I want to get all these parameters out of the way and then change just one of them to see the effect. That's the intent. I don't believe in making changes that you can't measure. Page, buffer, seconds was at 15 seconds. Like it took that. Also want to try, I'm just trying to get these all out of the way that might stop any sort of disk activity. And then cause the disk activity to kick in when I change a threshold down. Oops. Let's do that again now. Okay. There's a new one here I don't know anything about too, file stream centiseconds. I'm going to ignore that right now. Don't know anything about that one yet. So looking at our system, we do still have a little bit of system time and kernel time running. Just trying to get a reference to what's going on. That's still that MetaCity, the GNOME desktop doing some stuff. My memory is all either free or cache clean. We take free away. So cache clean, I got 140 gig of cache clean. Out of curiosity, let's see, slab top. And look at how big buffer head is here. It's at the top of the slab right now. What we got there. A 4 gig buffer head describing that 120 gig of cache free. Now there is another thing in here I'm curious about. There's a page cache limit now, but this is not officially supported. So let me try something here. sysctl-w page cache limit megabyte equals, I'm at 100 gig. What's 50 gig? 50, 1, 2, 3. That would be, looks like 50 gig. Let's see what that does. In actuality, when I did a lab on these in the past, that came out to twice the value. Let me try dropping it down to 5 gig and see what that does. Not seeing any change there either. In reality, it might be a limit on growing, and since I'm already grown, it might not be limiting me, but it's not officially supported on these platforms, and I don't know if that's the reason I'm not seeing a change right now. Okay. Also, the bottom of page 9.3 has us going into the elevator. One of the reasons I used to do the bottom of 9.3 and increase NR requests is so that I could see writebacks more. Having a bigger I/O operation queue will give you more writebacks. Let me do that right now. I'll go into sys block, and I'm going into, well, anyway, in my case, I'm going into XVM1. Well, that's the log. I don't want the log. CD into queue, and cat the elevator. And that's 128 I/O operations on the elevator that are sorted and merged by default. Cat the scheduler. We got a no-op, a deadline, and a CFQ. The CFQ is the default. Remember that the ESC dev attr.conf file controls this stuff. This is a SGI implementation that can control the max DMA size, command tag queuing depth, and we're just looking at the scheduler here. So let me echo 1024 into, not that this is going to make any difference because I still have the per device, and there were 4 of them, and I'm right now not interested in writing into all 4 of them. Okay, let's just cat. I did take a 1024. All I'm trying to do is see if I can see the writebacks bigger. Okay. So let me run the, this time I just created a script. Don't think I even have permission, so it does look I do. Bring up top. There's the DDs running. CPU utilization, all system time. Well, there was a burst of reads, probably to read in some executable. Now we're finally hitting, there's the write-backs occurring. And we were hitting that at, looks like about 80 gig or 100 gig. Now I had set dirty to 50%, 256. That should have been a 125 kbyte right there when we actually started flushing. Let me get rid of cache clean here. Let me get rid of free. So these write-backs have started here. We're almost right here. And we're still in the 100 gig range, not the 120 gig range. So I am still flushing. Let me try to do it. And notice they're all sleeping on GET requests. I see the flush daemon. And one of the things here, on page 93 of the labs, when it says you're going to run this stuff, how long before flushing starts? There's not going to be a change. I'm not seeing the changes because there is a trickle background flush that's occurring right away. But then there's also an aggressive flush that I'm seeing in here. So notice I still got all this dirty data now, 100 gig of dirty data again, but I'm still got flushing going on. All the writes. And it's all inactive file cache. Nothing out on swap. I can see the Numalink traffic that occurred from those writes. The system time and the IO8, and we do have some IO8 going on right now. See if we can find that. The flush daemon itself is showing up as the IO8. Anything with that GET request is one of the types of WCHAN events that will get counted in my wait IO. So I just want to see now if I can change the flush intensity here. You can see it flushing. And this red is slowly going to the brown. Well, let's try a sysctl. See if I can change it to flush by age. Where was it here? There we are. Let's go to 6 seconds and see if we change the behavior of this flush. Now remember, I also have write-back centiseconds slowed down, so the flush daemon may not even be waking up at this point. I'm not expecting this to work. I'm just seeing if I can get some sort of change here. Let me check the write-back centiseconds. This is how often the flush daemon's waking up. And let's change that one. It was 500 before. Let's go 100. And again, no change. So I still see this dirty data flushing. It's flushing no matter what. This is what I was calling a background trickle sync. And I'm not seeing the effect of any of this. Let's try sysctl-w vm.dirty _ ratio. The smallest it can go is 5. Let me try dropping dirty background ratio. And did that affect our flushing at all? Still the same sort of write-backs. Oh, I do see some IO wait time kicking in here. That's probably the flush demon itself. Let's take a look to see what's waiting on IO now. And that's the flush demon. Oh, when it goes away, I'm still seeing wait IO time. I've got the Metacity and the GConfD as well in an IO8 situation. Let me go into crash. I'll look at PID 14595. Taking a long time there. Flush demon's the busy part. Oh, gzip, which is doing I/O. It's non-interruptible, unzipping the kernel, and that's part of our contention too. Wonder what happens if I slow down. Not seeing any change in my I/O wait just from slowing that down. The largest dirty ratio and background ratio can go to is 50. Okay. Try BT on 15289. Oh, looks like that one just finished. 55468. That one's just sleeping on the pole situation. Oh, my IO8 is gone too. Okay. So by dropping those back up, my flushing is now stopped. Having changed the dirty ratio, dirty background ratio, let's just drop this down. 5. No flushing occurring. I've got this dirty data sitting here. What I got there, I still have 60 gig of dirty data here. You can see where the flushing stopped right here. The write backs have stopped and the writes to disk have stopped. The IO8 also stopped. Bring up top. So I don't see the flush demon anymore. So let's see if we can kick that flush demon in again. I do have a background of 5 and a dirty ratio of 50. Background ratio did not change it. My dirty expire centiseconds also did not seem to change it. Normally that should. I should be flushing anything that's older than 6 seconds. Let me change my dirty ratio back down. And this is probably what's going to kick in the flush demon. Not seeing any change there. My write back wake up is still really big. shorten that. 500 was the default. And now I'm starting to see the I/O weight come back. But I'm waiting for write-backs. I'm not seeing any write-backs. No write-backs yet. So we do have something in an I/O weight state. Still looks like those Metacity and gconfd. So I'm not seeing any flushing of this data that's sitting here right now. Let's just CTL-A, grep for dirty again. Everything looks okay. $500 is normal for that one. Let's set this one back to, let's go to 30 this time. Let's set this one to 10. I think that's pretty much going to cover it. Some of these things, I guess I should get back to where they were. I do have an inventory, so I know what the defaults were. I'm just waiting to see if I can kick this in. I'm still not getting any sort of flushing activity starting here. A sync will do it. What I'm playing around is the sysctl parameters to see if they're going to be 30 seconds. Everything should be older than 30 seconds by now. I should see some flushing going on. Everything else looks okay. That's what I mean by this experiment is not predictable these days with the newer kernel that I'm working with. The last two update kernels have acted this way. The last PTF kernel that we had was fine. Okay, PS. Look at the flush daemon. The T on 8877. So that's in a schedule state. It's got work to do. We've told it it's got work to do, but it's not seeing it. There are some trickle white write-backs occurring here, but we're nowhere near what we were before. So I'm just going to wrap this up here and try another sync. Sync should kick it in right away. We've got all that dirty data sitting in memory, and now we're kicking into the flush daemon. So normally when I'm playing with dirty ratio, dirty background ratio, expires centiseconds, I can see this effect more easily. After this is done, I'll reboot, and tomorrow we'll start off with clean settings. I don't have anything more that I was going to demonstrate today. Tomorrow I want to move all this into a CPU set situation and get into affinity, dplace, dlook, CPU sets. And also look at I/O and slab in a CPU set context. Okay? So I'm done for today.
Okay.
This is going to take a while to, even if I try to boot the system, I don't want to just do a reset. I would corrupt my file system. I have to wait for this data to get cleared out of memory. wait for the flush to finish.
Mm-hmm.
So I'll play around with this a little bit tomorrow, but at this point I'm done for the day. So thank you for your patience again. Send me email with questions. Now I'll get you that PM chart description here in the next hour.
Okay, great. Thanks very much.